The,
I
you
think
can see
everything, yeah, everything should be ready.
So just tell me,
Perfect.
Natasha, when I can start, and
yes,
I will
sure.
use the video. Okay.
Sure.
And nice to meet you, Natasha. You're new.
Yeah,
to
nice to meet you. Yeah. Yes. Joined 1 month ago.
So you were already at the AGM?
Yes. Yeah.
Great start.
Yes.
Yeah. So you can start, Jeremy.
Thank you.
Free-form micro-optics have the capabilities to revolutionize industries. Imagine automotive lighting that is perfectly aligned with the design of the car, or lighting solutions that provide better energy efficiency, better light distribution, and perfect aesthetics. Imagine all AR and VR capabilities with better resolution, feeling more realistic, yet the device reduced to a size that you don't even realize you are wearing. Or improving your home with luxury and smart windows. That is the power of free-form micro-optics. The ability to create optical shapes in any form you want, completely miniaturized for perfect integration. Opening up new opportunities for security and branding, optical communications, consumer electronics, and more. And now imagine that this can be done with equal or even better specifications than conventional systems, and at lower costs. This is why PHABULOuS has opened up the one-stop shop in freeform micro-optics, making this technology now easily accessible to everyone who wants to implement it, proving a full supply chain of world-class freeform micro-optics specialists. We can take you from design to prototyping and into pilot production for full product life cycle, including design, modeling, origination, tooling, and manufacturing services. Some have already paved the way by integrating freeform micro-optics into their product portfolio. Are you ready to take the next step in your product development? Make it fabulous. And contact the one-stop shop for freeform micro-optics at info@fabulous.eu. We are fabulous.
Good afternoon, everyone. I'm Jeremy Picot-Clement, Technology Manager at EPIC, and I'm really pleased to moderate this fabulous workshop of today on freeform micro-optics for lighting application. So we'll talk and learn about freeform micro-optics technologies through highly relevant speakers today on two different sessions. The first one focuses on design and fabrication, and the second one will be on application. So the aim of this workshop is for you as participants to get the maximum information of PHABULOuS, the European pilot line for the manufacturing of freeform micro-optical components, and also get answers. That's why I warmly invite you to ask any question you will have after each presentation. And we have also Jessica Van Eck, Managing Director of PHABULOuS among us, so she will be pleased to provide you all details you need regarding the project, PHABULOuS project. So for this workshop, 7 speakers with a focus on freeform micro-optics for lighting application. So why a focus on this kind of application? So we can see since now many years a growing demand for lighting products. There is a real need today to improve lighting infrastructures in terms of power efficiency, consumption, of course, but also in integration and miniaturization. So we can see also in innovation, this market is interesting for us since it's constantly evolving with new and innovative lighting products being introduced regularly on the market. So it's important for companies to differentiate themselves by introducing innovation in their strategy. And actually, from micro-optics can be a solution to reach these aims. Freeform micro-optics present also several advantages compared to conventional techniques, as giving access to compact and efficient optical system, reducing the number of optical components required, and enabling new kind of design. This technology improves efficiency as well. It can be designed to improve the efficiency of light sources such as the LEDs, for example. It provides a better light control by giving the possibility to control the direction of light more precisely than conventional techniques. They can produce a variety of beam shapes and control the speed and intensity of light. And last but not least, customization. So indeed, freeform micro-optics can be customized for a specific lighting application. And this customization is important since it's one of the strengths of European competitiveness in an industrial world where mass manufacturing is actually dominated by Asia. So about this workshop, here we can find the agenda. So we'll have a fabulous introduction by Jessica Van Eck, Managing Director at Fabulous. And after this, we'll have the first session on advanced techniques for FFMO, for micro-optics fabrication. So first presentation with Mark Villans, CEO at Villans UPMT, followed by Nolite Chan, Sales Director at Phasix, and then Christian van der Sluch, Director at Friptic. And we have also a second session mainly focused on application with an R&D with Ursula Palfinger, Senior Scientist at UNM Research, Christian Statscher, R&D Engineer at Sissenbacher, Katharina Keller, Director Optics at Zumtobel, and Ralf Lutz, General Manager at Leopil. So thank you very much for attending this workshop, fabulous workshop. And still you can find here our contacts. So my contact, Jeremy Pico-Clement, and Jessica Van Eck email. So feel free to contact us after this workshop if you have any question. And now I would like to give the floor to Jessica Van Eck, Managing Director of Fabulous, for the introduction.
Thank you, Jeremy. So I think you already gave a really nice introduction to Fabulous. So thank you for that nice video. And so yes, Fabulous is the pilot line for the manufacturing of freeform micro-optics. And as Jeremy mentioned, so Fabulous is a project. It's in the Horizon 2020 program and it's coordinated by CSEM, dedicated to the manufacturing of freeform micro-optics. And as part of the project, we also already established a legal entity, which is the Fabulous Pilot Line Association. So this I am managing. And this is as a first entry point to the customers and also to continue the services after the project. And our main goal, both from the entity and the project, is to create this pilot line for the design and manufacturing of freeform micro-optics and to unify the Europeans, RTOs and industrial partners into this pilot line. So within the scope of the project, we focus very much on UV imprint technologies. We do that in 3 pillars. So we have SUS micro-optics that can manufacture the optics on wafer scale, morphotonics on roll to plate, and nanocom on roll to roll. And then connected to that, we have CSEM and UNM Research. They can do the design and the prototyping in a way that we know we can reproduce in mass volumes with these replication partners. We have VTT for the integration, Fraunhofer FEP for coatings, CI for their silicon etching capabilities, and then Wieland UPMT Lazea Power Photonic as originators, and of course supported by EPIC and Amires for the dissemination and project management and website, etc. And as Jeremy also mentioned, very much focused on freeform micro-optics. So that means the benefits of freeforms, but then in a microscale. So no symmetry constraints. And the reason why we decided to do this project is because we've seen that there's a great increase in the amount of patents and articles that are published around freeform micro-optics, and we wanted to make sure that this technology becomes easily available. So that also brings me a little bit to the next slide, because without Fabulous, you would need all these different companies that offer all these different services. And so you would need a company that can help you with the design, especially design for manufacturing, then the origination, possibly tooling, the replication, quality control, integration, material selection, etc. So the idea behind Fabulous is that all of this is available through a single entry point. We have one NDA covering all these members, and we make one single contract for all the services. And so with this, we have all these different services that we can offer. As I mentioned, we have some special design tools also developed within Fabulous, really aimed at design for manufacturing, so that we know that any design or any prototype we make, we know can be produced in large volumes. We have, I think, at least 7 or 8 origination technologies available. We have partners that can do the tooling, so make the tools for the replication. We have partners that can do all material tweaking, and we have a lot of metrology inside Fabulous. Of course, all aimed at the replication and the integration. And we started the project already with a few companies that were looking to implement freeform micro-optics. So you see here the use cases, solid state lighting, transportation lighting, automotive lighting, micro displays and luxury. I'll take you through them really, really short, because some of them will also be, you will be hearing from them today. But so for the solid state lighting, we've been working with Sumtopol. You can see here a little bit already of the mastering of application. For the transport lighting, we have been working with Seisenbacher. So you see here also different phases that we have been able to do within Fabulous. With Hella, we've been working on the automotive lighting applications. So you see here some of the things we've done. For the micro displays with micro OLED. So you see here some examples. And then I think one that is also really nice, which I didn't see on the schedule today, is Swarovski. They, of course, are known for their luxury, and they made a really nice design. And you see here a nice light box using a freeform micro-optical structure. And on the left top, you see also this tool that we've made to create these kinds of structures. So all of this is something that we've already done. But of course, this is just one little glimpse of all the possible applications for freeform micro-optics. So there's a huge range of markets where you could be using freeform micro-optical components. And I think what is very interesting and important to mention is that if there is any company that is looking to implement freeform micro-optics, that right now we have an open call that will run until the end of the year. We will have cutoffs at the end of every month. Which means there's funding available for companies that want to also start implementing freeform micro-optical components. The funding is up to 90%, depending on the company size. And you can find all the information on our website under open call. And if you have any questions, of course, feel free to reach out to Jeremy, myself, or Ton. Ton is the technical coordinator, both of the association and the project. And with that, I would like to thank all the partners in the project, and of course, Photonics 21 and the European Commission for the funding. And I would always like to end with, micro-optics is fabulous. So thank you for this opportunity to present our capabilities, Jeremy, and I look forward to a really nice session today.
Thank you very much, Jessica, for this introduction of Fabulous. So now let's start with you, Mark Philance, CEO of Vidance UPMT. So you can, the floor is yours. We can start your presentation, Mark.
Yes, thank you. Let me share my screen. I suppose it must be this one. I have two instances, but I think it's this one. Okay, is this okay? Is everybody?
Yeah, you can start.
Okay, so hello, everybody. Thank you, EPIC, and thank you, Fabulous, for giving us the opportunity to present our technology. As everybody has understood, in the Fabulous project, there are a lot of technologies involved, and one of the functions that is very important for replication processes is about mastering. And we are in this project for diamond machining of masters. And this, we have a unique process which I want to present to you today. As you can see on the right, a number of structures as an array. This is typically what is fitting to our technology. So when we talk about nano imprint replication, as I said, and as was seen previously, is you start with the master, and the master is machined or is made by other technologies. The technologies in the presentation of Jessica were grouped as the origination technologies. And traditionally, on the left side, you see there are a lot of lithographic solutions, which I will not go in details of, but it's comprising etching processes, UV curable materials, etc. And in the center, you see another process, which is also used into Fabulous, which is a laser-based process, using a laser to ablate the material. Two companies are providing these services, Power Photonics and Lasea, and we are providing on the right side a chip removal process, which is a cutting process using a diamond tip to machine mostly metals, but also plastics, and provide with what we call ultra precision accurate masters. And when we speak about ultra precision, it is really what let's say the extreme precision that you can have, which is also used for your cameras in your smartphones. Okay, so that's the advantage of this diamond machining process. So let's go a little bit into the details of this technology. As I said, it's a chip removal process, and I want to distinguish diamond micro milling and diamond turning. So the micro milling process is where the tool is rotating, a bit like a drill bit, and the diamond turning where the tool is steady and where you make like a spiral on the tool, on the part that is rotating. You see in this table that the two processes can be used, but when you want to have the maximum of accuracy, you would prefer diamond turning. But of course, if you want to make very complex surfaces like arrays, it might be an issue to do that by turning. That's why diamond micromilling is, let's say, well, very much used also for making machined surfaces. Okay, so, but you see for roughness, for example, with 2 nanometers RA, you get really the absolute best quality out of diamond turning. So what you would like to know is, how can we then use, for example, diamond turning to make these optical surfaces with that quality? And that is what we provide. So we have developed a technology, which is an add-on technology for diamond turning, which is capable of sequentially addressing every surface of a lens array as a single lens on the axis of the machine. And in this way, we at the end come up with an extreme accurate array of lenses. And well, it is resumed a bit here with some images. So when you see an image like this, which is an array, with this technology, we would machine every lens individually as if it was a single lens. And so it's every lens is machined on the rotation axis of the machine. Of course, we cannot only make lens arrays, but also arrays of single lenses, which is also a nice feature for the production in mass of such lenses. Finally, what we do is we provide with 8-inch masters where that are fully populated. And in this case, for example, in this image, you see a number of MLA structures, and these are machined with this technology. So they are about, I think, 10 or 20,000 lenses on this master, and you will see a little bit of the accuracy of this. So the capability of this is to machine any surface that can be machined by turning. Let's say any lens surface that can be machined by turning as an array. And okay, I'm not going into all the details here, but you have like all the accuracies that are similar to, again, to what you can have in camera systems. What are the applications? Lighting, of course, consumer electronics, automotive lighting, and one of the examples that is given very often is the BMW carpet. Healthcare, small lenses here can be produced in mass with this technology. AR, VR, automotive headlights, all these processes typically use these kinds of masters. As an example, you see here in the image a free-form surface of an MLA where all the lenses are different. So this was for a VR application, and you see that the form irregularity of every surface can be 300 nanometers PV, so very, very low, with a very low roughness. And I think, well, it's the only technology to do that. Again, the image of the complete populated master of 200 millimeter. We have been developing this technology to, let's say, the complete accuracy requirements that our customers ask, which are not only for a lens, but also for the array, also related to the position accuracy. So they want, of course, that every lens on a 8-inch master, every lens is positioned at a sub-micron accuracy, which with this technology can be done. So lens to lens accuracies below a micron on this surface can be done. So we think this is now a ready technology for mass production, which allows to in a deterministic way to rapidly produce such masters in a very efficient way. So we are waiting, of course, for challenging designs that we can do. Freeforms, why not? Non-free forms also, of course, are welcome. So I think that I have consumed almost my time. So maybe there are questions that I can answer. So I will be pleased to do that.
Thank you, Mark, for your interesting presentation. Yes, so if we have any question from participants, you can raise your hand through Zoom, of course. And yes, we have a first question from Andrea. Andrea, please, you can ask your question.
Hello. Yes, it seems like a very impressive technology. Thank you very much for that very interesting insight. My question would be, can I think of the process as a sequential process? So you do one lens after the other, and what time would I estimate for such a lens array on a 8-inch wafer?
Yes, so indeed, it's a sequential process. So we always say, if we can machine one single lens, we can machine the array, but we would do that lens per lens sequentially. It is the process takes some time, as you mentioned. I would say magnitude 1 minute, 2 minutes per lens, about, depending on the size of the lens, on the size of the tool bit that we can use, on the features, of course. But we have a very, let's say, the lens, when the lens is free form or the lens is rotation symmetric, of course, that has also some impact. But we have optimized our technology, so it's not so much impacted. In fact, we can almost machine free form lenses as fast as non-free form lenses. Okay, so the technology takes some time. If you want a full populated master, can be a month of machining. can be day and night. But let's say this is a very much automated process and also a very safe process, because we have developed all the technology to avoid any drift during the process over that long time, and we are capable even to remove the master and put it back and remachine or continue the machining without having any impact on the positioning accuracy, for example.
Very interesting. Thank you very much.
Thank you, Andreas, for the question. Any other question? Please raise your hand. In the meantime, maybe Mark, I have a question for you. Can you just tell us more about how you were involved in the PHABULOuS pilot line?
Oh, yeah, we were asked as to provide our services, which are unique and which were known by some of the partners in the pilot line, because they felt that diamond turning was definitely needed as a mastering technology, because of course about when this accuracy is needed. In some applications you really need this accuracy. In some applications in lighting can be that it's not needed, but in some applications in lighting, even if the form accuracy is not as accurate as for a camera, still you do not want, for example, stray light coming from let's say from some roughness of the surface, for example. And this is definitely what our customers for the lighting processes always say to us within, for example, the PHABULOuS project. They say, wow, for us, it's also all about the roughness, okay? Coming with the roughness, such a sharp surfaces, that is what they want, in fact.
Thank you, Mark. So just to remember that you are a partner of PHABULOuS, of course. And yes, we have another question from Yvan, please. Yvan, Institut d'Optique. Yvan, you are muted.
Sorry, thank you. Could you please come back on the slide where you explain how your technique, the DPI technique, works? Because I didn't get this part. I mean,
okay, I tried to do that. Oh, are you still seeing me, or?
Yes.
No. I mean, now you're
do that again. Probably, I don't know why. Okay. So you want me to go back to?
Well, I'm just, yes, please. Could you please re-explain the principle and what differs in this technique from the other two techniques that you explained previously?
Okay. So let's say, first of all, as I mentioned here, on the right side, we have a chip removal process by cutting. So using, let's say, a conventional tool for cutting. Only this tool is a diamond tool to obtain the best possible roughness. Okay. So I suppose you are aware of that.
Yes.
So in a diamond process, mostly you would do turning, because this gives you the best surface.
Yes.
You have, like what you see here in the image, the black block is in fact is a rotating spindle on which you would position your part and then machine that part. Okay. But when you want to not make one lens, but let's say an array of lenses, of course, you cannot have easily every lens with its optical axis aligned with the rotation axis. Okay.
Yes.
Which is the ideal configuration. So what you see in the image is between the part and that black box, you have some blurry image, which is an add-on technology that we possess, that we have developed, which allows us to shift the part that you see on the right side near to the cutting bit, And so we can move this part away from the center so that we can address any surface of that plate as if it's to machine there a single lens.
I see. I see.
So it's an add-on technology with 2 axes principally to an ultra precision machine.
Okay, thank you very much. Yes, thank you. Very interesting talk. Thank you.
Thank you, Yvan, for your question. And yes, if you have no other question, thanks again, Mark, for your presentation. Thanks a lot. And let's move with our next speaker, so Nolan Chan.
Yes.
Physics. So Mark, if you can stop sharing, please.
I can do that.
Yes, perfect. Thank you. And Nolan, you can start.
Okay. This one. All right. Okay. So thanks for the introduction and the invitation to speak today. So I'll be presenting a metrology technique. Actually, we'll use more on the parameter that is wavefront and how we can use that to obtain the optical function or optical informations on the micro optics that are made, typically as was presented before. So to do this, I will first present in a couple words the company, so PHABULOuS, and what we do, and then move on to an example of a use case, which is, I think, more concrete or easy way to explain. So PHABULOuS is a French company that is 20 years old, and we focus on wavefront measurement devices. So designing, developing, and providing wavefront measurement-based solutions that are using one technology in particular that is called quadri-wave lateral shearing interferometry. In this presentation, I will typically present solutions that are based directly on the wavefront sensor and that is implemented on a regular microscope. We also build other kind of solutions so that typically our customers or partners can have access to complete solutions, including the source, the optics, or even completely automated machines for testing more complex assembled systems. So our solutions for testing micro optics is typically plugging our wavefront sensor, so at the correct wavelengths, for the correct spectrum directly onto a regular commercial or homemade microscope, which is here, a bright field microscope. We do this in an easy way to obtain wavefront information from a setup that can be easily accessible. So when we replace the regular scientific camera or regular camera with a wavefront sensor, what happens is that the light will first go through the first layer in our device, which is a diffractive optical element that we call modified Harman mask, which is a 2D phase grading. This 2D phase grading will diffract the light and create 4 replicas of the beam. These 4 replicas would then arrive on the sensor chip that can be of different technologies, like CCD, CMOS, or InGaAs, or whatever. And on the image, then what we get is typically what we call an interferogram, which is here a 2D sine function-like pattern that is locally periodic or slightly deformed in periodicity. And what we analyze is typically this frequency modulation on the interferogram to retrieve the intensity and the phase information. So we do this for 2 particular reasons. One is that we can use this solution for any wavelength that is compatible with the microscope. We have typically a technology that can work with the whole spectrum band of a given sensor technology. So typically in CMOS 400 to 1.1 micron. It is not sensitive to polarization, so you can also perform a measurement that gives you a phase signature or a phase function as a function of the polarization, which can be particularly useful for plastic optics. So it's easy to set up, of course. And this is also a way that can be easily integrated for mass production tests, so on production lines, because you always work with 2D images at once. So as I mentioned, what we measure is a wavefront. So in particular, the optical path difference that can be expressed this way, which is a difference of index of refraction times the thickness of the substrate or of the sample that the light is going through. And from this, we typically want to achieve a really nice and nanometric resolution. So the first problem is that when you work with a regular microscope, you work with the aberrations of the whole set of optics on the beam path. So you have this set of aberrations. On this set of aberrations, you have the ones that are coming exclusively from the measurement method, so from the microscope in this case. So what we do is that we subtract all the aberrations coming from the microscope itself, so that in the end, you have, of course, noise if you look at an area where there's no optics to check or samples to look at. But then when you go back to the area where you want to make the measurement, this way, this subtraction allows you to get a really nanometric resolution on the actual measurement that you want to perform. So of course, we measure the OPD, which is made of these two contributors, which is the difference of index of refraction and also of the thickness. So if you use this kind of orders of magnitude to give you an idea, we can achieve 10 to the minus 5 in terms of refractive index difference resolution. So this is more to explain how the system works and how we can implement easily the wavefront sensor on a commercially available microscope. And then if I want to use it, for example, on a microlens array that is displayed here. So here I have, in this case, so a microlens array of microlenses of f/1 of 250 microns focal length, and they work at 1070 nanometers, so 1070 nanometers. How it works is that we take this full image with the different microlenses, we extract the information for one particular sample, and on this one, we perform an analysis to obtain for each one of them, of course, the intensity and the phase map. So in this particular case, we will focus rather on the phase information in order to retrieve at first the focal length. So to do that, we take the full phase information and we decompose it along the Zernike polynomials, which enables us to isolate the focusing function of the microlens. So we use the polynomial that we call defocus. From that, we can derive the radius of curvature of the wavefront. In this case, in the way we implement it, this wavefront curvature is equal to the focal length. We make this measurement a couple of times in order to have an idea of the repeatability. And so when we do a repeatability measurement, we try to remove and replace the system. And then from that, we obtain a standard deviation of about 1 micron for a value of 215 microns. And on top of that, we can also push the Zernike filtering analysis a little further and isolate the what we call low frequencies. So in this case, it's the Zernike polynomials up to the 7th order and the higher frequencies, which are typically the rest. And from that, we can see that on top of having the simple information of what is the focal length of every single microlens, we can go deeper and try to understand also from that if there's astigmatism, if there's spherical aberration, if it is intended, and how does it compare to the design. And so this is the different kind of information we can get from a one-shot measurement. And here we can retrieve the orders of magnitude, which are in hundreds of nanometers. And if I want to go over another idea, which is trying to make a measurement on a polarization sensitive component. So here I choose, for example, a metalens component, and typically want to perform the measurements by having a rotating polarization as an input. So here, this enables us to obtain a varying phase function, and really, as once again, have an idea of how the phase function evolves with the polarization and compare it to the design to optimize either the manufacturing process or the design directly. So here we can see that I start with a focusing meta lens and make it commute or change into a diverging meta lens. And this is all possible because the wavefront sensor is not polarization sensitive, so I can choose freely how I want to perform the analysis. So the idea is really, I wanted to show how the wavefront sensor can be used in different kind of applications for testing micro optics. So you can either consider the optical function as I did, or either consider them as lenses and check their focal length. We can also have access directly to refractive index and also check the refractive index evolution for different polarization. It is implemented quite directly on any regular microscope, which gives you access to a really good resolution and something that can be easily done. And this doesn't require any particular complex optical system. So this can be done as a prototyping tool or to understand or to troubleshoot any prototypes. So I'm glad that this is the different examples that I can show here for refractive index mapping or different kinds of waveguides characterization, which can also be useful in micro optics. So I guess that would be it for my presentation. And if you have any question, I'd be glad to answer them.
Thank you, Nolan, for your presentation. Thanks a lot. So do we have any question from the participants? The room. So Nolan, this product you just shown has been adapted for micro lens analysis, or it's the same that you use for conventional lenses?
So what we generally do is we don't need to touch the hardware, but we touch the analysis part, for example, to be able to perform some large dynamic range analysis on particular micro optic system.
Okay, so you don't touch the hardware, it's the same, but you modify the software, the analysis. Yeah. Okay.
Yes, because we always have the data. The problem for us is how do we retrieve, how do we interpret the information for this particular cases.
Is the analysis of freeform micro optics is something that you have already done, or because you talk a lot about micro optics, but what about freeform micro optics?
So for freeform, so we work a lot with micro optics on one side and freeform on the other side. This is also something that I would like to push together in order to have a collaboration on this kind of optics. So indeed, we have experience in both separately, but together, not yet.
Okay, great. Yes, please, Katarina from Zoomtobel, please.
Yeah, one question. What is the maximum surface angle or gradient you can measure? So how steep can a surface be? What is the angle? So is it only flat lenses, but also very bulky lenses?
These can actually be really bulky. So it depends. So, okay, actually, as long as we have signal, we can find a way to retrieve the information, because there's no definite answer to what is the steepest angle, because we can input by simulation what is expected, and this will improve the dynamic range of our system. This is how we work with freeform optics, which are, of course, not micro, but larger freeform optics. So this is something that we've done in the past, and we can go really, really far So if you have an example of design or of optical function that you'd like to measure, we can typically take it and input it in the measurement method, so that you will see the difference between what you expect and what you get, which improves the dynamic range for us.
Thank you.
Thank you, Katarina, for the question. Any other question, please? Okay, so thanks again, Nolan, for your presentation. Thanks a lot. And now let's move to our next speaker, Christian van der Sloot, Director at Triptych. So Christian, so I will share my screen for you.
Thank you. Yeah.
You can start and I will change the slide.
Yes, thank you. So I'm with Triptych, and this presentation is more on the applications and design of the freeform micro lenses. So we talk about some examples. We discover a problem, and for that problem we have a solution. So it's not all the problems, just a design problem and some use cases. So if we go to micro lenses in the marketplace, Jeremy, next slide, please. We see, for example, an example that also Reinhard has presented on the EPIC AGM last week, car headlights. And we believe that not only in headlights, but in many more in-car applications have opportunities for micro lenses and many more. So what's the problem? Why don't we make them? Well, besides production, where Fabulous is a fantastic mechanism to get it produced, also the design of freeforms is time-consuming and therefore also costly often. Because the light sources need beam shaping, and freeform lenses are, in our view, the best and smallest way to shape the beams from various light sources. Next slide, please. So we have a solution for freeform microlenses, which is in-house developed. So it's not something that you've seen anywhere else. We have an in-house developed methodology and toolset, which is focused on calculation of freeform lenses on axis and off axis in any size, so including freeform lenses, even if there are multiple in a row. So it's in-house developed, it's completely different, and we are connecting to production partners to ease the production. Next slide. Yeah, so there's a couple of use cases, and I will also tell you about some use cases that are not on the slides. First one is lighting. On the left-hand side, the top picture is a car headlights that we've seen before. On the right-hand side, you see some other in-car applications where micro lenses might be used. There could be many more actually. Then on the picture in the right in the middle is a lamp. The big lamp is an office picture or an indoors picture of a house, and below there's an office picture. These pictures tend to be very big, or in some cases ugly, perceived to be ugly, and that's why we believe that micro lenses could be playing a role in lighting indoors and offices as well, outside of cars. On the next slide, we see some other applications. And here I also want to tell you about a medical application that we get questions from. And I will later on tell you something else that's quite slightly more, less complex. So first, the medical application, which is on the slide. We get questions, and maybe you can follow the picture on the right with me. There's a light source that could be a micro LED or a laser, and people want to have a homogeneous spread over on the completely right-hand side over a piece of tissue, and we can do that with the application of usually two freeform lenses. So from left to right, you see the light source, you see a freeform lens. Out of that comes the freeform lens make the light source light into transforms it into a perfectly collimated beam. And the second freeform lens can then be used to spread the light homogeneously or more or less homogeneously over the piece of tissue. So far, the medical application. We also get a couple of questions, and I've read a paper, I've seen a paper of it at SPIE that, for example, LiDAR also has a light source. And with a freeform lens, you can extend the LiDAR range. So this is not on the slide, but this is a question that might pop up. So the LiDAR range can be increased by up to 2 kilometers in range. So that's fantastic. And we believe a micro lens can help there as well. Now, on the next slide, you see some other examples. This is where we use, it's quite small, but maybe not smallest, where we have a perfectly imaginated off-exit example to show what our technology can do. We can, on the right-hand side, you see freeform lenses. And in a working distance of 5 millimeters, we can magnify the picture by 10 with a numerical aperture of 0.4. We do this with reflective optics. This is just another example. This is maybe a little bit out of what we talk about today, but this is something that we can do also in bigger scales. Now, I hope, next slide, please, Jeremy. I hope you like the presentation. Yeah, we are perfectly open to questions. Jean-Bernet is also on the call. Yeah, so this is basically the presentation. I hope it is of any value to you.
Thank you, Christian, for your presentation. So any question, please, for Christian? You can raise your hand through Zoom. So Christian, just a short question from my side. So do you have any product already on the market, or?
We are working with well, we're actually working with a laser company on and we're working with a company that is a chip for cameras, a camera chip where we focus the light on a very tiny chip. This will be on the market. We hope the design is finished by this summer.
Okay. Yes, Ralph from Leo, please.
Yeah, hi. Nice presentation, thanks. I wonder, it's for point sources, I would imagine, right? The algorithms.
Not particularly point sources, but light sources. Yeah.
So then, but they need to be small because otherwise you get too much light around.
For micro lenses, that is the case. That's
yes.
True. For micro lenses, yes. Yeah.
Okay, second question. Do you have a business model, or does your business model include offering the software?
No, at this time not. It's been years of development since 2020. At the moment, we are a licensing company, so we design and license the lenses.
Well, yeah. Thanks very much.
You're welcome.
Thank you, Ralph. Thanks a lot.
Thank you for your question.
Any other question, please, for Christian? And if we have no more questions, thank you a lot, Christian, for your presentation. And let's move. Thank you. Thank you very much. And let's move with our next speaker, Ursula Palfinger, senior scientist at UNM Research. So now we are going to explore R&D and also application. So Ursula, you can share your screen and start your presentation, please.
Yeah, can you hear me well?
Yes.
See everything fine. So hello to all. Thank you for the invitation to speak at this workshop. So my name is Ursula Palfinger from UNM Research. We are part of the PHABULOuS Pilot Line, offering different kinds of technologies, but today I would like to concentrate on upscaling via step and repeat UV imprinting. So some short words about UNM Research. We are a non-university research organization. We cover topics from human and medical research over IT, economics, and manufacturing technologies. We are located at several places in Austria and have altogether about 500 employees. but I come from the Institute Materials, or the long title Institute for Sensors, Photonics and Manufacturing Technology, with about 100 employees, 5 research groups. It's led by Paul Hartmann and located in the southeast of Austria. We see ourselves as technology provider, material and process developer, and offer applied research for prototyping and small series demonstration along the value chain, more or less, of micro-optics, microfluidics, bionics, and printed electronics fabrication. Within the PHABULOuS Pilot Line, we do several things like optical simulation combined with master and material design. We do a lot of origination with the main focus on laser-based methods. We offer upscaling of small originated areas. And finally, also do batch and roll-to-roll replication. But in this talk today, I would like to concentrate on our upscaling capabilities. So why do we need upscaling? In many cases, origination delivers limited areas or master sizes. So the reason is mostly given by limited writing times, especially when it comes to freeform 2.5D patterns. Origination can get very complex and last for days or even weeks, as we heard earlier, for some square centimeters. And on the other hand, industry for sure targets large areas. We want to cover displays, illumination setups, parts of rooms, and even buildings, photovoltaics. And upscaling tries to fill the gap from the small scale master towards a large area flexible stamp. So for this, we have at hand, and as we call it, large area foil stepper. So it's based on a wafer stepper, but with customized large area stage and several other add-ons. So we can work with flexible or rigid substrates, sized 300 times 700 millimeters maximum. And this is also as well in line with the required shim size for our own roll-to-roll replication. Generally, we work with some foil-based substrates to generate a flexible polymeric master shim that afterwards can be transferred to nickel as a durable replication tool for roll-to-plate or roll-to-roll. And I would like to show you 3 upscaling tasks that we have done for different PHABULOuS use cases. For 2 of the use cases, so Zumtobel and Seisenbacher, Katharina and Christian will give a specialized presentation afterwards in this session. But let's get started with the first use case. It's led by Seisenbacher. They develop interior lighting solutions for the railway industry. And within PHABULOuS, the partners developed FMLAs, so freeform microlens arrays, with the idea of generating a homogeneous illuminance pattern when these lenses are placed over an LED array with a certain distribution. So after optical simulation and designing, one single microlens was originated, like shown here. It's as large as about 15 times 30 millimeters. Origination was done by grayscale laser lithography. And the idea of the upscaling task was to fabricate stripe-like arrays of 12 freeform lenses each with 20 millimeters distance center to center. So in principle, a simple pattern replication on a larger area, but requiring a very good positioning, so finally perfectly fit to the locations of the LEDs. And simulation gave us about 20 micron positioning accuracy tolerance over the whole area. So what we finally do is to fabricate a working stamp for the step and repeat upscaling process. So in this case, we had a grayscale litho master that we molded into nickel. And from that, we did a UV imprint on quartz to fabricate a step and repeat working stamp. In this case, most effort in the upscaling was done on optimizing a reproducible filling process of the pattern that contains different step heights, can be seen here with quite an angle variation. And the lens had a maximum height of 50 micron. So finally, we could well produce these 12 lens stripes as a resin on foil polymer shim. So that's what's coming out of our step and repeat upscaling, which at the end was converted to a nickel shim by CSEM for roll-to-plate replication. And we did an independent distance measurement and ended up with distance deviation values between 3 and 5 micron, and an average value over all lenses of about 4 micron over our whole active area of 300 times 300 millimeters. So this is more or less representing our stage positioning accuracy without using our alignment system. And with that, we have been well within the specs for this use case. Another upscaling with totally different requirements was done for Swarovski. So as we know, they focus on sparkling crystals for decoration, luxury, and lighting applications. And within PHABULOuS, we developed freeform micro-optics to create sparkling areas, not by using real crystals, but by an imprintable pattern, creating a large area sparkling foil. So this was the main target of this use case. The pattern was simulated and designed by Swarovski, and we finally ended up with randomized facet structures with a maximum height of 200 micron that could be originated via laser ablation in quartz by our pilot line partner Power Photonic. And they managed to create the master in a way that the patterns ending on the right side were exactly continued from this point on the opposite side, because here we targeted for a real seamless area upscaling from this 20 times 20 millimeter master to a final area of 140 times 260. You can see that already here. We have here 4 step and repeat imprints positioned with a nominal distance of 500 micron. And we see an image from the optical microscope of 2 imprint edges with the gap. And we can also immediately see that the patterns continue from the left to the right, fitting very well. So after imprint optimization for this very high pattern, that also has to include a very good definition of the imprint edges, the task for us was to minimize the distance now. And you can see here already 4 imprinted fields. So these are 2 times 2 fields with 0 distance, and their visual appearance in different angles and illumination. So even by the naked eye, which by the way, unfortunately, is very sensitive to straight lines that disturb a pattern, we can hardly see the stitch lines. So on the right here, you have a macro photo where you can get an idea about the stitch quality. So the stitch, one stitch is here, and the continuation of the faces from left to the right. And this was finally the result. So we fabricated 13 times 7 fields, seamlessly imprinted onto a flexible substrate foil, reaching the required field size for this use case. And again, this polymer shim was galvanized by CSEM, and the pattern was then roll-to-roll imprinted, at uranium in this case, into a resin with high refractive index and dispersion to result in a sparkling crystal-like appearance. And the last use case I would like to show you is the application of Zumtobel. They go for innovative indoor lighting solutions and targeted a wall wash application. So freeform micro-optics that produce a homogeneous light distribution on a wall when placed over a spotlight. The pattern was designed by Zumtobel, and again, it was clear here that originators will not be able to directly fabricate the whole requested area of 200 times 200 millimeters in this case. And with again having a view on seamless upscaling during the design phase already, we decided to go for a hexagon-shaped master here, with the idea of having not too sharp corner angles and supporting this special type of structure with seam lines that are as invisible as possible. The master again was originated via laser ablation by Power Photonic. Again, you can see here first single step and repeat imprints, so with the nominal distance first. And finally, after like 18 or 20 improvement cycles, the optimized seamlessly stitched structure on the right. And as a final result, we have here the 200 times 200 millimeter upscale field. It's resin on foil. I have to say, working with the hexagonal master was new to us. It needed some basic changes in our grid design, but we saw that this approach can be really beneficial for the stitching result, especially if type and design of the pattern allow for this strategy. So to summarize, we offer the upscaling of micro and nanostructures to fabricate large and flexible polymer type shims. These polymer shims are stable in subsequent galvanization processes. Therefore, we target all roll-to-plate and roll-to-roll type replication or production processes. Good single imprint or master field sizes for us are somewhere between 10 × 10 and 50 × 50 millimeters, whereas we did glass slide size already as well, for example, 25 × 75 if needed. The maximum shim size that we can offer at the moment is 700 × 300 millimeters. So with that, I would like to thank you. Do not hesitate to contact the Fabulous front office with your upscaling tasks. So I will be happy to answer your questions if you have some.
Thank you very much, Ursula, for your presentation. Thanks a lot. So any question for Ursula, please? Maybe I can start, Ursula. I have just one question regarding Fabulous. Can you tell us a bit more about your experience working, with partners through the Fabulous Pilot Line?
Sure. So more or less the Fabulous Pilot Line, as we saw, developed very well in more or less working together, or more or less getting well-used results from one partner to the other. So I think in the first years, this development was really nice. So and now I think we really can offer more or less all tasks that are needed to realize the value chain for freeform micro optics. But it's also possible to more or less request one sub-process like simulation or origination. So more or less we offer the whole value chain now. But also maybe also a single step if needed.
Thanks, Ursula. Any question, please raise your hands for Zoom. And if we have no question, it was a perfect introduction for our next speaker. Thank you, Ursula.
Thank you.
And now let's start with Christian Stacher, R&D engineer at Bacher. So Ursula already presented a few things about these projects for Fabulous. So Christian, I will let you start your presentation, please. The floor is yours.
Yes, of course. Hello, everybody. Thank you for having me. I hope you can already see my screen.
Yeah, you can stop.
Perfect. Yeah, also on behalf of Seisenbacher, a warm welcome to everyone who joined for this online workshop. So my name is Christian Stacher. I'm working at Seisenbacher as an electronics engineer. And I was one of the lucky ones, let's say, who could work on this exciting project. So to begin with, let me tell you shortly what Seisenbacher's business is. Seisenbacher is an Austrian interior supplier for the railways industry. As you can see in the pictures, we do a lot of components which are in the inside of the train and which directly affect the comfort of the passengers, such as handrails, partition walls, tables, seat structures, luggage racks, air duct systems, sailing systems, and last but not least, the lighting, which is mostly integrated within these sailing systems. But sailing systems are for sure our core competence, let's say. By the way, micro-optics is something we were not in touch before Fabulous, which makes us kind of unique as use case member within Fabulous. What I want to say is that you don't have to be an expert in micro-optics to realize a project with Fabulous. Well, this is a slide, or this slide is just to show you one reference project from many others from us. I thought since Fabulous is an EU-funded project, I show you the new tram in Brussels. For the trams in Brussels, we delivered a sailing system with integrated lighting, air ducts, and air diffusers. So if you ride the new trams in the future, you can say, I know the company which did that beautiful sailing, hopefully. Yeah. So, well, Seisenbacher was chosen to be one of 6 use case partners in the pilot line. Within the Seisenbacher use case, our aim is to make a large area direct lit luminaire using freeform micro lens arrays to improve the luminance uniformity, a thinner form factor, and or a reduced LED amount. The luminaire should be developed for the railways market, mainly, of course. Somebody of you may wonder why they don't use edge-lit luminaires, since this technology would meet all these requirements and is already state of the art. The reason is that edge-lit technologies can't be used in railways applications, unfortunately, because of fire and safety standards and regulations. And the problem is the material of the light-guided plates. And that's the reason why we try it with direct lit applications now. And by the way, large area luminaires for railways seems to be quite trendy. So a few words to the functional principle. As you can see at the picture on the right, there is an additional freeform microlens array layer. It is shown in blue here. And it's between the LEDs and the diffuser. So here are the LEDs and here is the diffuser. Due to this, the emitted light coming from the LEDs get redistributed so that the entry side of the diffuser is homogeneously illuminated. As a result, we should have no visible LED spots and a homogeneous appearance of the luminaire while improving the distance to height ratio, also called DHR. And the DHR is a ratio between the LED pitch, so the distance between the LEDs, and the height from LED to diffuser. So yeah, this is the idea and the concept behind it. We already have heard that the PHABULOuS Pilot Line offers services from the idea or the design until the fabrication of the micro lenses, and even integration. As I said at the beginning, that Seisenbacher hadn't any experience with micro lenses before. We really took advantage of nearly every service PHABULOuS offers. Every service which is marked with these green boxes was used by us. So we had the idea and the requirements for application, but starting with the design over mastering, upscaling, choosing lacquer materials, quality control of each step, roll to plate replication, and some minor parts of the integration were done by partners of the PHABULOuS Pilot Line. Seisenbacher itself was responsible for the electronics, the integration, and building of the demonstrators. Yeah, within the next slides, I want to show you some details about each step and progress. Yes, some words to the requirements. We decided that our luminaire design with integrated freeform microlens arrays should be based on a real project. You can also see a crosscut picture, a crosscut picture on the right, which is one of the two luminaires of the sailing system, which can be seen below. We decided for it because it's a linear luminaire with a very broad diffuser, which is very common and also easier to realize for proof of concept. The diffuser width was defined at 80 millimeters. The distance from LED to diffuser should be 27.2 millimeters. The diffuser characteristics were defined exactly, for example, transmission of light. Yeah. The luminaire should be tunable white ready, which means color mixing of a warm and cold white LED should be possible. And of course, the luminaire must comply all the relevant standards for railway applications. Yeah, in the next slides, you will see a lot what you already have seen within the presentation from Ursula Palfinger. The design of our lenses was done by Ioneum Research. They used an algorithm which generated a Fresnel-based lens, considering all requirements and desired LED distribution. The LED pitch, which is the distance from one LED to another, with in this case with same color, was set to 40 millimeters. And considering a tunable white solution, the LED pitch is actually 20 millimeter, but with alternating LED color. The generated microlens itself can be seen at the picture right. It is approximately 22 millimeters in length and 40 millimeters in width. The maximum feature height is 50 micrometers. So it's very flat to the Fresnel-based design. The distance from LED emitting surface to the microlens was set to 3.5 millimeters. And at the two picture at the bottom, you can see the difference of light intensities on the diffuser entry side between the luminaire of the real project without microlenses and the luminaire with the free-from microlens arrays integrated. Both pictures are ray trace simulations done by Ionium Research. On the left picture, you can see that you just have a very bright stripe in the middle, which fades out along the width of the diffuser. And on the right side, you can see the improvement of the light distribution on the diffuser entry side when adding the free-from microlens arrays. So the big benefit is that with the FMLAs or free-from microlens arrays, you get much more homogeneous appearance of the luminaire while improving the DHR. Yeah. Coming to the mastering and upscaling process, when the design is finished and the parameters are known, the pilot line decides which method out of their portfolio could be the best for your application. In our case, for mastering, it was grayscale laser lithography by Ionium Research, which is done by Ionium Research. You can see a very nice picture of our written master optics at the right top. After that, the master was galvanized and molded, resulting in a stamp used for step and repeat upscaling. With this process, our desired microlens pattern, consisting of 12 lenses in a row, was done with a high accuracy in positioning. You already have heard it by Ursula Palfinger talking about plus minus 5 microns. The output of that process is the so-called polyshim, which you can see in the picture at the bottom right. This was then galvanized and additional coated with an anti-adhesion layer. So you see, in summary, you see a lot of steps have to be done, but we're not finished yet. To commence the roll-to-plate replication process, it is necessary to produce a flex stamp molded from the shims. This stamp will serve as a tool to imprint the replicas in the roll-to-plate replication process, which will be carried out by Morphotronics for the Seisenbacher use case. A 2 millimeter polycarbonate paste substrate will be utilized, on which a UV sensitive lacquer will be applied, and the lenses will be imprinted. On the right-hand side, you can, on the right-hand side, 2 images of the replicas are displayed. In the upper picture, small crosses can be observed on the left and the right side of the lens. These crosses are implemented for an optical vision system to aid in cutting. When cutting the FMLAs, it's critical to reference the optics and not the edges of the substrate. At the picture in the left corner, you see a finished FMLA which is already cut and ready for integrating to the luminaire system. So coming to one of my last slides, we also have built 2 types of demonstrator within the use cases, within the Seisenbacher use case. We have built these, we call them laboratory prototypes, which are small scale prototypes for testing. They are 1 meter long, easily accessible and easy to handle. Furthermore, they fit much better into for example, temperature chamber or an shaker for shock and vibration tests. The picture in the middle shows a little bit the inside, the inside of the laboratory prototype. You can also see our integration concept. Spacing elements ensure a distance of 3.5 millimeter between LED and FMLA. The FMLA is therefore directly mounted over the spacing elements on the PCB, which keeps the tolerance chain very small. The right picture shows the full-scale demonstrator, which is a component of a real project from Seisbacher. It has 2 luminaires on left and right side. At one side, the original lighting from Seisen, the original lighting without PHABULOuS FMLAs is implemented. At the other side, the lighting with PHABULOuS microlens is implemented, analogous to what you can see at the picture in the middle. So the full-scale demonstrator should show the difference between original and PHABULOuS lighting system. Yeah, and the last few words to the results, experience, and outlook. Regarding results, we achieved a quite nice system or system concept, which could be an alternative to edge-lit luminaires, especially for railways. Furthermore, we have achieved a full functional integration design, which complies to all the strict tolerances and requirements. And of course, we have built the demonstrators. Yeah. The team within the Seisenbacher use case also achieved a full process chain walkthrough of the FMLAs, beginning with the design until the finished cut replicas. Yeah, and first results of lighting tests are promising, but to be honest, there are still some further iterations of the FMLAs necessary to bring the homogeneous appearance to the luminaires as desired. And yeah, regarding the experiences, I can only say that there are highly competent partners in the field of micro-optics within the pilot line. Furthermore, they have a broad spectrum of knowledge and resources available. And yeah, it's really a one-stop shop where you come with your requirements and they do the rest for you. And for the outlook, of course, finalization is clear, and as next to scale up to a real large scale application. So now we did this linear luminaires, but we want to make, yeah, let's say bigger luminaires, bigger in the surface and in the width. Yeah, so that's all from my side. I hope this was informative and interesting for you. I also hope that you have seen which parts of the project were done by the pilot line. Thank you for your attention, and of course, feel free to ask if you have any questions.
Thank you very much, Christian, for our presentation. It's interesting to get so much information about your project. So thanks a lot for this. Any question for Christian? Please raise your hand. Regarding your participation to the PHABULOuS Pilot Line, you already gave us some information, but about your experience, was it smooth to work with partners? Was it everything was clear for you? Did we get good support from the PHABULOuS Pilot Line? How was it from your side?
Yes, I can only repeat. It was really good to work with the partners, and as I already said, there is such a big or broad knowledge, broad spectrum of knowledge there. So you always have partners where you can ask if you have any problems. And in summary, I have to say runs smooth. Yeah.
Perfect. Thank you, Christian. Any question, please raise your hand. Okay, so thanks again, Christian, for this interesting presentation of this use case of Fabulous. Thank you very much. And now we can move to our next speaker, Katarina Keller from Zoomtobel. Katarina, please, you can start the presentation. Thanks a lot, Christian.
So how? I hope now you can hear me well.
Yes.
And see my screen. Yes. Okay. Yeah, from my perspective, I would like to tell you a little bit about Fabulous and what we experienced. Zoomtobel is a aluminum manufacturer. We are also offering lighting solutions, so including lighting design and also controls. We are based, or our headquarters in Austria, but we have distributed sites over Europe and the US. My presentation has 3 steps. So in the beginning, I still would like to repeat what's freeform micro-optics out of our perspective and how was the creation process. This is again about Fabulous and all the different steps, but always with some remarks, what we experienced so far, and then our use case there. So freeform micro-optics is really something where you don't have any symmetry restriction anymore. So it can be really absolutely randomly. And this is also how we use it in lighting. It can be transmissive or reflective. Of course, we can do reflectors by that, or we can also, just a moment, please. Excuse me. And yeah, reflectors and lenses. And of course, we can also have lens arrays where each lens is a freeform lens and which we have also in an irregular grid assembled. By the way, the last thing we really did in Fabulous. In imaging, which is partly the case what we do also in illumination, there's one big advantage to use freeform optics because you can reduce the number of elements you have to use. So you can connect the image forming and the aberration correction in one part. This is very useful. In non-imaging optics, which is mainly used in illumination, you can achieve also very asymmetric light distribution, what we also have done inside Fabulous. And of course, if you go to micro optics, always you have very lightweight and elements which consume very little space. These are one of the 2 big advantages of freeform micro optics, what we see for illumination. So again, the overview of all the processes involved. Modeling and simulation probably will depend on the company where you work with. Some have their own capabilities, some work with partners, but still freeform designing of really freeform optics, it's a very demanding task. Also in illumination, where sometimes very demanding requirements are there concerning the target distribution. Then comes the origination, what we heard a lot about, also from UPMT in the beginning of this session. Then the generation of the tool. This again could involve quite some steps. This we also heard before. Then the replication with the different techniques, and in the end, the integration. It could be very demanding or it could be less demanding. What we have seen already with the use case of Seisenbacher, there the preciseness have to be very high. So for modeling and simulation, usually you could start with array mapping, that you really see what is the flux distribution or illumines or luminance distribution of your light source, which you have to map to your target area. This might be the first step. And then different programs have different algorithms. Some calculate directly, others have optimization to get in the end to the real NURBS surface. But still, even there are quite some programs around coming to the real optics or the real element in the end in the cut. It's still quite demanding. And of course, if you have your part then modeled in the cut system, you do the simulation to see what kind of, if it really is what it was calculated, and of course also to make some simulations, maybe foreseeing some deviations from the actual part then from your design. And maybe you can already do some, for example, compensation of shrinkage or other things here. Then we come to the origination. I like to repeat. So we have this diamond micromachining by UPMT, then the laser micromachining, femtosecond laser ablation, grayscale laser lithography, and two-photon absorption. And of course, as a use case partner, it's quite demanding. What are the right techniques? And I think this is exactly what the pilot line is about, that if the user comes with a problem or with a task, more to say, to choose the correct technique. And this is also what we learned in the last 3 years, that not all techniques really map to your requirements. Each of those techniques have their advantages and disadvantages. For the replication, this is the same. Of course, you have some possibilities in wafer scale, which we used in our use case. And this is that you have a very high precision, that you can have very high structures. But of course, it's not so industrialized as it's, for example, roll to roll. And the roll to plate is also very interesting for illumination, because to have a rigid part in many cases in luminaires is an advantage. All of those, I can say from what we learned, is the replication very good. So if you have any damages inside your master or inside your tool in the end, you will see in the part as well. What they might differ is a little bit maybe about the shrinkage. And here we are already with the quality control. And this is still a really demanding task. Usually you would have or have to have done the quality control after each step. But of course, if you have structures, for example, that's why I'm asking before about gradients and steep angles, this is still not really solved in all scales, I would say. We have some equipment in our community, like laser scanning, microscopy, SEM, white light interferometry, and profilometer, but still it's not that easy. And also to have a really good data transfer, so that you really have first your simulation, then the master, then maybe the tool generation, and so on, that you really have a closed loop. What happened after each step, it's not really me too, so it's what you have to look for. Then materials, there was also quite some material testing going on. So materials which are very likely to use for imprinting, which are good there, might not be usable in application as demanding. For example, in illumination for transportation or automotive have quite some high requirements, but also we in illumination are here in sometimes in very harsh environments, so this has to be tested. And geometrical measurements, that's what I already mentioned. So now to our use case. As mentioned before, we actually took one of the most demanding tasks we have in general illumination. This is wall washing. So you have here a very asymmetric light distribution depending on the size of the wall and the situation where the luminaire is, and also the difference between the luminance in the top and the bottom of the wall is very limited. So, and you have also to have sharp or quite straight edges. So this light distribution is really strong, asymmetric, and quite demanding to reach. You see here a picture of a luminaire which was realized with a bulky freeform mirror, and this is what we wanted to do with a lens array. Other challenges we see in general lighting, of course, we have large sizes, so we need not only like in head-up displays or in other applications, even in automotive, the size is not so big, but in illumination, of course, we need a large size. Then we have long lifetime, so the materials have to be very good. And then maybe into contrast to other applications, illumination, it's very cost sensitive. And the combination, of course, of large sizes and cost, it's quite difficult. And then Mark was mentioning maybe the demands of surface and shape control and surface roughness might not so be big in general lighting. It depends. It depends really. So we have some deviations which we could still use, but we have in other fields where the deviations have to be very, very small and the surface has to be very perfect. Yeah, so in the end, we will have lens arrays as a result, and this we will of course use also in combination what we see with the light source in illumination, so where we can really tailor our spectrum what we use. And I think this combination in the end is really very beneficial for general illumination. Thank you.
Thank you very much, Katarina, for this great overview of the different steps of fabrication from micro optics. So any question for Katarina, please raise your hand. Maybe I can ask you something more general, Katarina. So in your opinion, what is for you the main challenge for a mass adoption by the market of freeform micro optics today?
Yeah, so in illumination, we still have to see where we can come to with cost.
Mm-hmm.
So we have to compete. So this span from optical elements for general illumination is the price span or cost span is very broad. But we have also some suppliers from the US and China, which are very, cost driven and where we have already quite some interesting products. But I think to have in Europe the possibility to really tailor your own surface and make your own target distribution is very beneficial.
Great. And the same question as for the speaker, what was your experience within Fabulous? Can you tell us a little bit more about this?
Yes. So I can just repeat what Christian was saying. So all the companies have a great deal of experience, and also over the last 3 years, I think this was growing. So the task of all use case partners haven't been easy. So for each partner inside the pilot line, I think they made some improvements also in investment, what they have done now to be even better. Even quality control was also a big topic. So I was very happy to work with them.
Perfect. Thank you again, Katarina, for this presentation. Thanks a lot. And last but not least, now we can move to our next speaker, Olaf Lutz, General Manager at Leopi. And thank you again, Katarina.
Yeah, hello. I think,
hello.
Yep, now we can do it. All right. Okay, so thank you very much. It's a pleasure to be here, and I try to be very interesting. So this is about freeform optics for operating rooms. So it's a lighting application. It's ergonomic lighting, and we will see that there are a few things that haven't been mentioned yet. For example, norms and regulations. It's a collaboration between my little company, then FF Optic, and Chromaviso, a Danish company. There are two operating theaters, I mean, in principle. So we have what we like, I mean, like most of us, we know operating theaters from the receiving end, I guess. So where we are often is open surgery. That's dominated by high brightness and all these squads of people doing this. And then more recently, minimal invasive surgery. You can see that the lighting scenario is very different. We try to put that here, and it's in the open surgery, we get norms that tell us what to do, like how bright to be, and also what brightness not to exceed, which is the interesting part. So for example, you want some light on the walls, but not too much. And you want to avoid glare, which is a very important factor. In the minimal invasive surgery, this standard does not apply, and the illuminance is 15 times less. So people there are concentrating on the task at hand. They look at screens. They don't even look at the body. They want what we list here, multicolor luminaires for optimal visual conditions in flexible environments, meaning that every surgeon does it in a different way. They want the colors to be flexibly rendered, and ergonomic lighting here means that the surgeon looks at a monitor with red behind the monitor, red behind himself, so that he doesn't see reflections of any kind, which is probably the equivalent to glare in the open surgery. And the green behind the monitor reduces the contrast, so he feels less stressed. The operator. I mean, these operations still go, even though minimal, they go for hours and hours. So how can we help as a company that doesn't run a hospital, but as an optics company? So freeform design, I think Katarina explained that quite well already, is kind of this various stages of ray mapping and returning and repeating things. So we get, or we decide on a desired light distribution. We do that in Excel actually, and then we get a detector data which we convert into ULUMDAT, which tells us how the distribution should look, and from that we can directly calculate the freeform, the shape of the lens, which is done in a software called FF Optic. So we don't need to know anything about the optics before we know the target. So where the target description is the interesting part, and then from there we create optics. When we combine it with a source, then there's all kinds of issues, of course, because sources are not as they should be, and there is light where it shouldn't be. But what we really can see is that if we have done this wall and floor distribution, getting the target distribution, and then the optics here as an array of lenses. When we repeat this, we get to a reasonable distribution that we feel looks okay. So that's, I mean, here is the visual impression, but of course, there's also all the data behind it so that we can see that we fulfill these norms. And then it's really a back and forth fulfilling glare, for example, which here is fulfilled, but especially in places where you can't change the conditions, meaning you cannot put the light where you like the light fixtures where you want them, then it's not an easy task to fulfill these things. So you adjust and redo. Here in detail, you have an existing benchmark case that looks like that, which is too much glare, which is too bright on the walls, but is a rotational symmetric luminaire. And then we do the freeform, clearly tilting towards the wall, and we get this visual and a lot less glare. So we consider this a success from the optical design part. We also want the colors to be present. So if now comes this array thing that everybody talked about, you need to replicate and put things together. And we would want to do that so that the colors that need, as you remember, only the 100 lux, whereas the whole thing needs 1500, we want this to be flexible and to be operated within one luminaire. So we again have a hexagonal way to put these to stitch them together, to tile these lens elements, and we have here different colors that allow us this flexibility for the operator. Manufacturing is possible. I give you here another photo of another example where we had done hexagonal lenslets on a fairly large scale. That's, what is it, A3 kind of. And the funny thing here is that they are both sided. So you have, it's a silicone on glass technology that is not fabulous, but could be. And it's on both sides of the structural element, the glass, fulfilling also the fire safety and all those things. Right. Thanks very much. I think one note while I'm speaking on what Katharina said. We had a recent automotive project where we did diffractive optical elements also on glass, and that was there the tolerances became the problem. It's not really so much the surface and things, but because there's always some stray light, and maybe it appears a little weird when you directly look at it, but usually in the distribution in the far field you don't see it. But what you see is when tolerances become when they are overshot, and that's maybe the difference between the imaging and the non-imaging thing. But otherwise, it's pretty similar, I believe. Yep. Thank you very much.
Thank you, Ralph. Thanks a lot for your interesting input. Any question for Ralph, please? By the way, did you already heard of a PHABULOuS Pilot Line, Ralph?
Yeah. I was involved in the early stages.
Okay, great. Any question from the participant, please? Okay, if you have any question after, okay, Katharina, please, from Zoomtable.
Just a quick one. If you have different LEDs with different colors involved, how do you deal in this project with colored shadows? Do you have any, or how do you do that?
You call them color, what, like cross cross lighting, or what is it? Sorry.
Yeah, I mean, if you use a lens array and you have different kind of LEDs, do you get any colored shadows? So it can blocking.
Okay, we believe not, but of course, the concern is that when you look into the light, you will still distinguish different colors. But on the wall or on the floor, you shouldn't see anything. Though we cannot. I mean, I cannot guarantee that because it's it has not been built in this form.
But this is accepted by the customer to have colorful luminaire, let's say.
Yeah, as you said before, the main issue with illumination is the cost.
Yeah. Okay.
Yeah. Thanks.
Thank you, Katarina, for the question, and thank you again, Ralph, for your participation and for your presentation.
Pleasure.
Thanks a lot. And I would like to ask maybe to Jessica before to end this meeting. We'll give you the floor, for the ending words. So we're on time.
Okay, thank you so much, Jeremy. I think, yeah, I mean, it's a great moment to say that we still have this open call, and especially with the cost and the development cost, funding can be up to 90%, which means, we can really help you on the design for manufacturing and create a master at highly reduced cost, which also would mean that future applications can already be covered for the portion of, for instance, using the same master. So I think this is still very interesting for any potential users in the call today. And another thing is that besides the Fabulous Pilot Line with the partners that I presented earlier today in the presentation, we also have an ecosystem. So this is available for any company offering any kind of solutions in the area of freeform micro-optics or micro-optics in general. They can, on the website, there's a tab called Marketplace that brings you to the ecosystem. So any European company can put in their organization and then put in their services, which is a great place where we want to unify any, the European ecosystem as a whole. So I see we already have some companies here in the meeting today that are there, but also some that are not yet. So we welcome any company to join the ecosystem free of charge. And yeah, I think for now the open call is very interesting. So Ralph, I already sent you also a message to see maybe we can talk about being an interesting use case for a pilot case for Fabulous. So yeah, and if there's any questions still here by the participants about Fabulous or the services or the open call, let me know or send me an email. I will write my email now quickly also in the chat. So feel free to reach out and let me know if we can support you with anything.
Yeah, thank you very much, Jessica. And yeah, thanks to all the participants, of course, and all the speakers of this today's workshop. Thanks a lot. And if you have any question, feel free to contact us, Jessica or myself. Of course, we'll be pleased to support you in any case. Thank you very much to all of you. And Jessica, yes, if you can put your email address.